And
And
so,
yeah, I think Ray really take it away.
sure. So this is our VIP project. We're the modeling process of neighborhood change group. You can go to the next slide. So just what we're going to talk about, we're going to talk about first Dr. Martinez's paper, what we've done, what we've changed to it, the revised methodology, where we're at now, what we think is our strengths and weaknesses, and what plans we have for the future. So just for some background, we've worked with Dr. Martinez this entire semester, and uh, our work is mainly based off of his paper he published beginning of this year, which mainly talks about how his motivation for this paper is infrastructure, mainly transit infrastructure, impacts people. Designs are made with a set of standard, like a status quo, but he wants to address, well, what if that standard changes? And planners should take into account people infrastructure interactions when designing these buildings or transit. So this entire paper just goes on and talks about that and how the effects of infrastructure affect people. And if we go to the next slide, the main issues that he addresses in this paper are gentrification and how gentrification leads to um what's it displacement, sorry, yeah. And so um the idea is that as planners begin to add new infrastructure, especially transit, add new freeways, transit lines, private investors come in and invest, make new buildings, shopping centers, things like that, in communities where there's usually underserved populations, low income, minority residents, and that causes and historically has caused gentrification. Historically low income minority neighborhoods are forced out, which leads to displacement. Rent prices are spiked. A lot of the community is displaced, and it's just something that's been going on around the world and especially here in Atlanta. And so for his paper, Dr. Martinez goes on to use something called no regret dynamics, which is just something where people are looked at as agents that incur a cost based on every action they take. And so all agents take actions at the same time, and the process is repeated until there's an equilibrium. And so the process I just described just goes as following. It's an agent or a person in this model is going to adopt a probability distribution. This probability distribution mainly acts as a way of saying, at this time step, what are the actions that this agent can take? So then the agent's going to enact a random action based on the distribution. So the agent's going to choose an action to take based on what probability he's chosen. Then we have other agents or adversaries in this scenario, in which also take other actions, and their cost of their actions is revealed to the agent. So this is saying that at the moment that the agent takes an action, they also know what other actions the other agents took at the same time. And so with that in mind, the agent takes a cost based on their action and the actions of other agents. And just to show what I guess what the simulation would look like on a visual model, this is from Dr. Martinez's paper, and it just shows how agents move around a certain neighborhood and reach an equilibrium based on a number of time steps. And so this cost function that I'm talking about, Dr. Martinez includes 4 components for it. He believes that the main 4 components that affect uh, people moving into different neighborhoods are housing affordability, which utilizes the idea of a Lorenz curve. Amenity access, he's just saying that a closer housing unit is to amenities, the more attractive it is. Community ties, there should be a similarity between endowment of the residents in a community and dwelling abandonment and upkeep. So is the housing unit in a state of occupancy or is it a state of abandonment? And it's a binary result. So what are we trying to address now? Can you? So at this point, we've decided this semester that we're going to use a case study. More specifically, we're going to use the Atlanta Beltline. And so we believe it's a great case study because there's a lot of research done on it, specifically from Georgia Tech. Construction of the Beltline is still ongoing. There's a lot of data, social demographic data provided, and the effects. There's already some portions completed that show effects of gentrification and displacement. And so what we're trying to do this semester, what we're doing differently from Dr. Martinez's paper is we've added a few factors to the cost function. So we've added a beltline indicator, which lets us know if the region that we're looking at is in the beltline, since we're caring more about the greater Atlanta region. We're using location cost. We're looking at agents distance from the centroids and mode of transportation. Centroids, we're referring to the different subregions of Atlanta and the Atlanta Beltline. And one of the big components that we're adding is the four-step travel model, which just for right now is used by planners to understand how much people travel between locations. It's a good way to understand how people move in throughout certain regions and zones, and allows them to know how much roads are needed to be open, buildings, and things of that sort.
So just for some context, when we do the cost calculation, as Rayleigh mentioned, there's a lot of different factors that come into play. This is just how we describe it in the code. We essentially consider affordability, the base location cost, community cost, accessibility, upkeep, as well as whether it's in the beltline or not. And then based off of that, we calculate a cost. And the goal is the agent wants to minimize its cost, so it will go towards things that are innately more attractive. Next slide. So as Rayleigh mentioned, we utilize a four-step model, but there is a very good reason why we need to do this. So one of the main motivations behind this project is that we want to simulate human behavior in the sense that we have these agents and we want to essentially see, given the existence of a beltline, how would these agents essentially switch their behavior and change where they relocate. And because of that, every time an agent incurs a cost, they have a choice to make as to what housing unit to go to. However, to decide where they go to is in of itself a complex process because of this human behavior aspect. So we would need some sort of model that can accurately replicate the human decision making behind where they would go. And so to that end, we have this four-step model because we need to distribute people across Atlanta based on their cost in a realistic way. And so what factors do we consider when we have this distribution? Well, one factor is definitely the vehicle type. Does this person or agent need the car or public transportation in order to get from point A to point B? As well as amenity density. So this is a new concept that we created during this semester, which essentially is a measure of how many amenities a region has. And the way we did this was on OpenStreetMaps. You can actually have tags for different buildings or whatnot, different regions inside a subregion, and we essentially get a count of the total number of those per subregion. And this four-step model has four steps, as the name implies. So the first step is trip generation. So essentially, we estimate where people want to go based on these amenity scores. So we essentially treat each amenity score summed up and divided by the amenity score for each individual region as the probability as for an agent to go there. So places with higher amenity scores would have a greater likelihood of people going there. For trip distribution, we use something called the gravity model based on the amenity scores and transportation costs in order to distribute the trips. Essentially, give agents a trip for them to go from point A to point B. From there, we calculated a modal split, and the modal split is essentially okay. What percentage of agents will use public transportation or cars in order to get from point A to point B? And then we finally do route assignment. Next slide, please. So this gravity model is essentially a way for us to calculate the attractiveness as a whole for a region. So what we have here is a math equation. I'm not going to get too in depth about what this is, but essentially what we're doing here is considering the net amenity score of a zone. We consider the number of trips that is produced from zone I, where we're going from I to J. Then we consider the number of trips from I to J, and then we consider the transportation cost from I to J. And then based on these variables, we create a we create or essentially calculate how many trips will exist from zone I to J. And the lower the number of trips indicates the lower the attractiveness of the end destination, and the greater the number of trips would indicate the greater attractiveness of the end destination. Next slide. So this is just some code stuff. I'm not going to go too in depth, but pretty much what we do is for generation of trips, we calculate an amenities probability by summing all the amenities and dividing each amenity score by the total amenities to generate a probability for that region. For distribution of trips, we essentially, what we do is we calculate a bunch of different factors that I talked about in the last slide pertaining the gravity model, and then based off of that, provide trips for all the agents. From there, next slide, please. From there, we do a modal split. So essentially, we consider how many agents here have access to a car, how many agents have access to public transportation. And based off of that, we would further split the distribution of trips based on those factors. And then for route assignment, that's essentially the final step where each agent actually gets a route. And then in the next iteration of the simulation, they will go ahead and move to that region that has been calculated based on the route, based on the cost that they've incurred.
Right. So because our simulation is essentially trying to model human behavior, a lot of the logic driven by the four-step model, we thought it best if we use as much live census data as possible and apply it into our simulation. And so what we did was to create our graph of the simulation, or Atlanta. We essentially download the shape files of all the census tracts in Georgia and filter it by the counties we want. For example, our simulation right now, it takes into account all the census tracts in Fulton and DeKalb County, which we get from the Tiger/Line geodatabases. And each agent in our simulation has a income attribute. And instead of assigning these incomes arbitrarily, we actually look at the census data. For example, just 2010, for example, there's 2020 data as well. But if in 2010, like 10% of residents had an income in the top 5%, then so would our agents. So this would be reflected in our model to reflect reality essentially. And so this is done by pulling, these are the two CSV files we pulled from the census website. It's just the median income as well as the total population to create the distribution. So essentially where we are right now with our simulation is that our code outputs a GIF which visualizes essentially the change of demographics over time. So each of those circles on the graph with the numbers essentially correspond to a different census tract, and the number is the population at that census tract at the time step. And so this GIF in particular is run up to 20,000 time steps, and each frame of the GIF is taken every 400 time steps of our simulation. And just to clarify, a time step is essentially an action, or each time step is when an agent chooses to move to a different location. So 20,000 time steps means agents are moving around 20,000 times. And this GIF in particular is run with 1,000 agents. And so I ran this on my laptop the other day, and fetching the amenities for all like 530 census tracts takes around 37 minutes, considering there can be like thousands of amenities in each region. And this is fetched using OSMNX from OpenStreetMap. And computing distances takes about 18 minutes on my laptop. But both of these are cached, so after you run the simulation once, all subsequent runs on your local device will take like 5 seconds for many of these distances. The simulation itself, however, if you run it with the parameters in the screenshot, it takes around 45 minutes because these parameters produce about 8 different combinations of parameters. So it's different. It's basically 8 different simulations. But the GIF creation and the creation of all these frames is what takes the longest. For one GIF of 50 frames, it takes about 20 minutes for just one of these combinations of parameters. And these runtimes is definitely something we need to work on for next semester. And one key part of our simulation is how modular it is and how adaptive it is. So essentially, I download the shapefiles from the census website. And so if you wanted to simulate an entirely different region, for example, different states or different counties and whatnot, all we would have to do is change those download links in the configuration file in our code, which is shown in screenshot. Just change those links to the desired shapefile, and your simulation will run with the desired shapefile. And similarly, you can get a different economic distribution from the census website. Again, it's just changing a link, and that will correctly change the distribution of income among your agents. So the simulation is essentially can be run anywhere that the census covers. And of course, there's a filter for the regions you want. So you can choose as many counties, as many whatever subdivided area you want. And just an example of uh, this is when we were running the simulation of a close-up of the Atlanta region, essentially. And so as you can see, the graph looks completely different. And all we had to do was replace the IDs of the desired regions as well as the download link. Another key part is that in our simulation, you can see that the green circles actually indicate which regions are in the Atlanta Beltline, and this process is automated from OpenStreetMap. All we do is enter the ID of these trails. So this is a bike trail from OpenStreetMap, and this is a railway from OpenStreetMap, both corresponding to the Atlanta Beltline. And this automatically marks which regions are in the beltline on our simulation, which does affect agent behavior. And so if you wanted to explore, for example, what would the behavior of Atlanta residents look like if the beltline expanded 2 miles to the west or 2 miles to the south? All we would have to do is get a trail from OpenStreetMap that reflects this. For example, if we could create a trail as well, that looked completely different than what you see on the map. We could run that in our simulation, and so it's really up to us how we want to experiment with it.
So regarding the strengths and weaknesses of our approach, so as Matthew mentioned, one of the strengths is that we take a very modularized approach to this problem, as in parts of the simulation can be easily reused. So for example, the four-step model is its own file that can be utilized for any other city for any other simulation. Not just city, even like subgroups, subcomponents, whatever you want. So that four-step model that was created was used for both a broad Fulton County to Cobb County overview, as well as the like actual Atlanta city. So it's very adaptable. Furthermore, our approach is backed by established human behavior approaches. So like no regret dynamics is an like an established game theory idea, and we utilize this in order to create our simulation, which gives us more validity. We also use a distribution system that is also established, the four-step model, which gives us even more validity. And we're able to produce dynamic visuals, GIFs, as Matthew mentioned. But we're also able to use other tools like we can use Folium in order to create graphs as well. It's just more time consuming, so we just stick with the traditional GIF. And then in terms of our weaknesses, we're limited only to the 2010 census data for training purposes, because the idea here is that we use this 2010 census data in order to get the best parameters for our model. And then we use this model to replicate or attempt to replicate the 2022 census data. And then based off of that, we essentially see how close we are. But because we only have one data set for this, the 2010 census data, we're pretty limited in terms of what we can use for training purposes. As Matthew mentioned, it is also pretty time consuming to run the simulation. 37 minutes were needed to generate the centroids, which can be quickened. However, I think the major pitfall here is that the API calls limited this. I spent a lot of time trying to multi-thread or multi-process the actual amenity density calculations, but for some reason we just kept getting stuck on like one subregion, and then that would cause a buffer, and then eventually we just ended up going with a single process rather than trying to multi-process, even though that's longer. um Additionally, we assumed that there was no immigration or emigration in this model. We're assuming all the agents are closed off in the Atlanta region, which is not really representative because people leave cities, come into cities. And then in terms of our transit, we limited ourselves only to car and public transportation. So in the future, that's something we can look at addressing, perhaps adding more forms of transit. Next slide.
Right. So for the next steps that we want to take next semester, at least the most immediate ones, first off, we want to make the GIF clearer and more readable because when the census tracts get small, you pretty much just can't see them behind just the big circles representing the populations. So we have to do something about that for sure. Um, in, in terms of functionality, these are the list of all the amenity tags that we're pulling from OpenStreetMap. And right now, the amenity score or attractiveness of a region is simply the density of all these amenities. So amenity count divided by area. But this is very, very basic and most likely not realistic. So we want to make it so that more desirable amenities, for example, a hospital or university, airport, is affects this score more greatly than say a museum or just a shop, right? Just anything we want, but we want to add weights to these amenities. And most importantly, we want to add a way to test the accuracy of a simulation. So as Devin said, we want to acquire realistic parameters based on the 2010 data and then using these parameters, run it with 2020 data and see how close to reality we can get. And this is currently in progress right now. We've made some progress on this, but it's not fine-tuned yet. So most likely we'll get this done next semester. And yeah, that's all.